Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 11: Wave and Field Generation. How ripples and fields are written in phi. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are now stepping across a significant threshold in Ep.9, the generative grammar. We have spent profound time in Book 9.2, exploring topological production, the realm where phi's smooth fabric can develop stable tears, giving us defects with automatic integer labels, dynamics governed by conservation, and statistics woven from the braiding of world lines. We have, in essence, learned how the universe writes its nouns, its persistent, countable things. But the cosmos is not only nouns, it is also verbs of motion, adjectives of quality, and paragraphs of process. It is filled with ripples, oscillations, fields that stretch and pulse. Today we enter Book 9.3, Waves and Fields. We leave the world of knots and return to the open ocean of smooth phi, asking a new kind of question, not about tears, but about ripples. How does the universe write its verbs of undulation? How does it compose the shimmering, waving sentences that carry light, sound, and information? This part, wave and field generation, how ripples and fields are written in phi, begins with a fundamental rule: dispersion as allowed combinations. Our anchor image for this climb is a grand pipe organ in a vast cathedral. Picture it: rows of pipes of different lengths, from towering giants to tiny flutes. The organist presses a key, air is pushed into a specific pipe. The pipe does not produce just any sound. It selects, from all possible vibrations of air, one precise note. A long pipe produces a deep, low hum. A short pipe produces a high, bright tone. The pipe's geometry, its length, its shape, its material, dictates which oscillations are allowed to resonate stably within it. It is a filter of possibility. The universe, in its holophase architecture, operates with the same exquisite selectivity. Every medium, every stage upon which phi performs, is like an organ pipe of a certain shape. It has rules about which rhythms in time, omega, can marry which patterns in space, k, to form a legitimate sustainable wave. This rule of marriage is the dispersion relation. Today, we learn how to read this rule as a core piece of the generative grammar. Here is the elegant puzzle of this part. Phi is continuous and can, in principle, change in an infinite variety of rhythmic and spatial patterns. Yet, when we look at the world, we don't see every conceivable ripple. In water, deep waves move differently from ripples. In a crystal, sound travels at specific speeds. Light in glass slows compared to light in vacuum. Why? What in the language of phi acts as the master tuner, the cosmic organ pipe, permitting some omega k pairings and forbidding others? The answer lies in the constitutive rules of the medium, which are themselves written in the grammar of phi. Remember, medium is not a separate substance. In holophase, a medium is a particular stable configuration or state of the phi field and its derivative tower, a paragraph of the cosmic story with its own internal logic. Think of it as a dialect of the language. In one dialect, say the vacuum state, phi might be very stiff, resisting certain kinds of curvature. In another dialect, say a solid, phi might be dense with a periodic structure. These properties, stiffness, density, periodicity, are not magical. They are expressions of how intense the changes in phi are, its second derivatives, its curvature, and how they relate to each other. The dispersion relation, often written in texts as omega equals some function of k, is the grammatical rule that emerges from this dialect. It says, in this particular story context, if you wish to write a wave sentence, the time frequency omega and the spatial frequency k must be related in this specific way for the sentence to be grammatically correct and dynamically stable. Let's explore this with our triunity lens, hearing the three echoes of a dispersion relation. The time echo of dispersion, rhythm and tempo. The dispersion relation dictates the allowed tempos of oscillation for a given spatial pattern. If you fix a spatial pattern, a specific waviness with a precise k, the dispersion rule tells you the omega, the pure tone at which that pattern can oscillate in time. For a simple medium, the rule might be omega equals a constant times k. This means a wave with twice the spatial waviness oscillates at twice the temporal frequency. It locks rhythm to pattern. The time echo is the permissible pulse, the heartbeat that the medium assigns to each spatial vibration. It answers, for this shape, how fast can it throb? The space echo of dispersion, pattern and structure. Conversely, if you fix a desire for a certain rhythm, a certain omega, the dispersion relation dictates the allowed spatial patterns that can carry that rhythm. It tells you the K, the tightness of the wave's wrinkles in space. In a complex medium, like a crystal lattice, a single time frequency might be carried by several different spatial patterns. The space echo is the permissible texture, the architectural blueprint that can support a given tempo. It answers, for this heartbeat, what shape can the medium take? The motion echo of dispersion, propagation and speed. Crucially, the dispersion relation determines how a wave packet, a localized lump of energy, a coherent group of waves, moves through the medium. The motion is governed by two key velocities derived from the omega k relationship. The first is the phase velocity, how fast a single crest of a pure wave moves. In our audio terms, think of it as the speed of a single, endless pure tones wavefront. The second, and often more physically important, is the group velocity. This is the speed at which the envelope, the overall lump or packet of waves, travels. It is the speed of a signal, of a pulse of light, of a water wave group. The group velocity is given by the derivative of omega with respect to k, a measure of how omega changes as k changes. The motion echo of dispersion is this choreography of propagation. It tells us whether different frequency components of a signal will travel together, preserving the pulse, or spread apart, dispersing the signal, and at what speed the information actually travels. This is why different colors of light bend by different amounts in a prism. They have different group velocities in glass. Now let's locate this concept on the master tree. We are on the foundational branch of wave production within Book 9.3, Waves and Fields. This branch depends directly on the first principles of the language, the definitions of omega, the time derivative of phi, and k, the spatial gradient of phi. It assumes we are in a domain of smooth phi, not at defect cores. It enables everything that follows in wave physics: the construction of wave packets, the phenomenon of interference, the formation of coherent fields, and ultimately the derivation of wave equations from deeper principles. The dispersion relation is the first filter in the wave generation process, the rule that separates possible wave sentences from grammatical nonsense. To make this tangible, let's scatter lanterns from across reality. A near lantern from music, the guitar string. Pluck it. It vibrates. It doesn't produce a chaotic noise, but a clear note. That note is its fundamental frequency, its omega. The spatial pattern is a standing wave, a single hump with nodes at the fixed ends. The length of the string, L, forces a specific relationship. The allowed spatial waviness, K, is proportional to 1 over L. The tension and mass density of the string then determine the constant that links omega to this K. The dispersion relation for a perfect string is simple. Omega is proportional to K. This tells you that higher harmonics, notes with more spatial humps, larger K, oscillate at exact integer multiples of the fundamental frequency, omega. The medium, the taut string, dictates the allowed omega K pairs. Change the medium, fret the string, shorten L, and you instantly change the allowed K, and thus the omega, producing a higher pitch. A middle lantern from communication technology. Radio bands. Your Wi-Fi router and an FM radio station operate at very different frequencies. This is not arbitrary. The dispersion properties of the atmosphere and of the materials in our devices are different for different omega ranges. Wi-Fi signals at gigahertz frequencies, very high omega, have a certain penetration and diffraction behavior, a certain relationship to their K in air and through walls. FM radio at megahertz frequencies has a different relationship, allowing it to travel farther and bend around hills. The medium here is the electromagnetic environment. The dispersion relation for electromagnetic waves in free space is omega equals the speed of light times k. But inside materials or complex urban landscapes, this relation is modified, creating bands where propagation is efficient and other bands where it is lossy. Engineers must design their systems to use the allowed, well-behaved omega k pairs for their intended medium. A far lantern from astrophysics. Neutron star oscillations. A neutron star, the ultra-dense remnant of a supernova, is a medium of unimaginable stiffness, a quantum fluid of neutrons under crushing gravity. It can oscillate or ring like a bell when perturbed. These oscillations are gravitational waves, ripples in spacetime itself. In our language, spacetime itself is a manifestation of the phi field's derivatives. The neutron star's extreme structure imposes a highly complex dispersion relation on these spacetime ripples. Certain omega k combinations correspond to fundamental vibrational modes of the star. When astrophysicists detect gravitational waves from merging neutron stars, a part of the signal contains the ring-down from these oscillations. By matching the observed frequencies, omega, to models, they can infer the star's size and constitution. They are effectively reading the dispersion relation written by the star's extreme phi configuration, testing the grammar of matter under conditions impossible to create on Earth. From the guitar's note to the Wi-Fi signal to the ringing of a dead star, a universal theme. A medium, defined by its internal structure, acts as a selective filter on wave motion. It provides a dictionary of allowed omega k word pairs that can be used to form coherent wave sentences. What then is the specific language role of a dispersion relation? It is a grammatical constraint on verb formation. It is the production rule that says, in this chapter of the story, this medium, if you wish to construct a verb denoting oscillatory motion, the temporal adverb omega and the spatial adjective k must agree according to this conjugation table. It is a rule of agreement between time and space, enforced by the narrative context. The core question this part asks about phi is, given a specific stable configuration of the phi field that we call a medium, what are the rules that govern the allowed small oscillations, the ripples, upon it? How does the medium's internal texture constrain the marriage between temporal rhythm and spatial pattern? We are moving from describing static or topological states to describing the rules of their vibration. What does the dispersion relation do in the generative process? It filters the infinite spectrum of possible waves, selecting a specific set of modes that the medium can support. It classifies media by their wave-bearing properties. Is it dispersive, non-dispersive, linear? It determines how signals propagate and evolve, predicting whether a pulse will maintain its shape or smear out. It links microscopic properties of the phi field, like effective stiffness or inertia, to macroscopic observable wave behavior. Now, stability and breakdown. The dispersion relation for small amplitude waves is a linear, stable property of a given medium. It holds perfectly for infinitesimally small ripples superposed on a stable background. It breaks down when the wave amplitude becomes large, introducing nonlinear effects where waves start to interact with themselves and the simple omega k relationship becomes inadequate. It also breaks down at boundaries between media or at scales comparable to the underlying granularity of the medium, like the atomic spacing in a crystal. Within its domain, linear perturbations of a smooth, stable phi background, the dispersion relation is a precise, predictive grammatical rule. This brings us to our unwavering commitment: falsifiability. The claim that dispersion relations emerge from the constitutive rules of a phi-based medium is a precise numerical proposal open to stringent test. The central claim. For any physical system successfully modeled as a specific configuration of the holophase field phi, the measured relationship between time frequency omega and spatial frequency k for small amplitude waves must match the dispersion relation derived from the phi grammar for that configuration. Furthermore, if we systematically change a parameter of the medium, for example, density, tension, coupling strength in the phi model, the resulting shift in the measured dispersion curve must follow the predicted quantitative change. Let's consider a laboratory classic: waves on a taut, flexible string. We set up a long string with controlled tension T and mass per unit length mu. At one end, we attach a mechanical vibrator that can oscillate at a precise computer-controlled frequency omega. At the other end, the string is fixed. We use a high-speed camera or a series of optical sensors to capture the shape of the standing wave that forms on the string at each driving frequency. From the video, we extract the spatial wavelength, the distance between two nodes or two crests. The spatial frequency k is then 2 pi divided by that wavelength. We repeat this for a wide range of driving frequencies, omega. We also vary the tension T in a series of controlled experiments, collecting a new omega k dataset for each tension. The pass condition, validation. The plotted data points, omega versus k, for a fixed tension, fall perfectly on a straight line passing through the origin. The slope of this line, measured from the data, equals the square root of the quantity T divided by mu. This is the exact prediction from the simplest phi model of an ideal string, where the stiffness is the tension and the inertia is the mass density. When we change the tension T, the new datasets produce new straight lines whose slopes scale precisely as the square root of the new tension. The phi grammar, in this simple case, predicts the linear dispersion relation omega equals the square root of T over mu times k. The data confirms it with minimal error. The medium's parameters, through the grammar, dictate the allowed wave combinations. The fail condition, falsification. The data consistently deviates from the predicted straight line. Perhaps the points curve, or the line, does not go through the origin, or the measured slope does not match the calculated square root of T by mu, even after careful accounting for known experimental imperfections: air resistance, stiffness of the string itself. Even more damning, if changing the tension produces a change in the dispersion curve that is qualitatively or quantitatively different from the predicted square root dependence, say the speed seems to depend on frequency itself in a way not captured by the model, then the simple phi model for this string is falsified. It would indicate that our generative grammar for this system is missing crucial elements. Perhaps we need to incorporate the string's bending stiffness, a higher derivative property of phi, into the model, which would modify the dispersion relation to omega squared equals t over mu k squared plus a constant k to the fourth. This would be a refinement, but if no such extension of the phi grammar could ever fit the data, the entire approach for that class of systems would be invalid. This falsifiability is our keystone. It ensures that the beautiful analogy of the organ pipe translates into hard numerical accountability. Let's cultivate a practical recognition skill. You can train your perception to see dispersion rules in any situation where a medium imposes a specific relationship between how fast something happens and how widely it is spread out. Watch crowd flow through different environments. The speed, omega, at which a density wave of people moves through a wide open plaza, the medium, is different from its speed through a narrow corridor or a bottleneck. The spatial pattern of the crowd, k, and its propagation speed are linked by the dispersion relation of the space, governed by its geometry and the rules of pedestrian motion. Observe the pitch of a voice in different gases. Helium is a different acoustic medium than air. It changes the speed of sound. When you inhale helium and speak, the temporal frequencies, omega, of your vocal cords remain roughly the same, but the spatial waviness, k, of the sound in the helium-air mixture changes, resulting in a higher perceived pitch because the dispersion relation, the sound speed, has changed. Consider the speed of a rumor in a social network. In a tightly knit, homogeneous community, a dense, regular medium, a rumor, a social wave, might propagate with a certain characteristic speed. In a sparse, fragmented network, a disordered medium, the same piece of information might travel slower and become distorted. The effective social dispersion relation is different, altering the link between the rate of spread, omega, and the network's connection pattern, k. When you notice that the rules of the game in a particular environment dictate how quickly a pattern can oscillate or propagate relative to its spatial scale, you are perceiving a manifestation of a dispersion relation. You are seeing grammar in action. We must connect this deeply to our Holophase journey. In the topological books, we saw how constraints, like being on a circle, lead to quantization. Here, in the wave book, we see how constraints, the constitutive rules of a medium, lead to selection rules. The principle is analogous. The architecture of the phi field's narrative context restricts the allowed stories. Quantization restricted defect labels to integers. Dispersion restricts wave modes to specific omega k curves. Both are forms of grammatical filtering. If you want to see the full mathematical derivations and exact equations behind this idea, the formal derivation of dispersion relations from linearized equations of motion, the connection to wave operators and Green's functions, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let's pause and see our place in the grand narrative of Episode 9. We have transitioned from the particulate, knotty world of Book 9.2 to the smooth, undulatory world of Book 9.3. We have taken our first step here by learning about dispersion relations, the rulebook for allowed ripples. This is the foundation upon which all wave physics is built. With this rulebook in hand, we can now ask, how does the universe write a localized sentence, a wave packet? How do these waves interact to create interference patterns? How do they lock together to form coherent fields that act as a single entity? These are the questions that await us in the subsequent parts of this book. Before we end, the mandatory zoom out to hold our scope. The dispersion relation, for all its power, is still just a rule about phi and its first derivatives, omega and k. We have added no new substances. We have simply looked at a specific stable paragraph of the phi story, a medium, and derived the grammatical rules for writing small oscillatory sentences upon it. One field, phi, plus its infinite tower of derivative questions. In this episode, we have journeyed from the first sentence through the engine of smooth production into topological production, learning to write knots and braids, and now into wave production, learning to write ripples and filters. The generative grammar continues to reveal itself, layer by layer, as a unified, coherent language. As we conclude, hold the image of the cathedral organ. Each pipe is a possible medium, a chapter in the universe's story with its own shape. The organist, the initial conditions and dynamics of phi, chooses which pipes to activate. But the pipe itself, its length and geometry, dictates the precise note that will sound. It filters the breath of air into a pure tone. The universe is this organ on a cosmic scale. The holophase field is the breath. The myriad media, vacuum, water, crystal, plasma, the social fabric, are the pipes. And the dispersion relation is the physical law of the pipe, the unbreakable rule that translates the breath of phi into the specific, allowed music of waves that fills our reality. We have just learned to read the first note on the sheet music. Salam and peace be upon you.